You can do it for high-dimensional data as well, and that's where Gaussian mixture models are actually useful. They're not used in 1D most of the time. So for high-dimensional data, what you have is you have real-valued data with d different attributes, and you're assuming that all of these, that every one of your data points came from one of k different sources, and each source in this case is a Gaussian in a d-dimensional space. So in 2D you might have a set of points, and maybe we want to fit two Gaussians to that. Right. So the algorithm proceeds exactly as before. You start out with your data points. You place two Gaussians with random means and random covariance matrices somewhere in space. So in this case, I'm just choosing to place a red and blue Gaussians like that. It's not a particularly good fit to the data, but EM will make that fit better. So, and again, I'm going to run through the same steps, only now we're going to do them in arbitrary dimensionality. Right? So the first thing is to figure out, I've got two Gaussians, how probable is each one of the data points under each of the two Gaussians. So again, if you're trying to make sense of it, think of a shooting analogy. I've got the red target and the blue target. Suppose I'm aiming at the red. What is the probability that my bullet lands here or there? Right, that's the number that you are computing, and that number looks like that. So the probability of the ith instance xi under Gaussian number c is going to have the following form. So this is just a normalizer so that the Gaussian adds up to 1. You don't have to worry about that. Then you have an exponential, and here is the need of the Gaussian, right? So look at what we're doing here. Gaussian number c has a mean, so that's the mean vector, a vector of the centroid for Gaussian number c. So we're subtracting the ith instance. We're subtracting the mean from the ith instance on the left side and on the right side, and in the middle we're multiplying it by the inverse of the covariance matrix. And remember, the covariance matrix, this covariance matrix is specifically for Gaussian c, so that describes the shape of the Gaussian. Right. So right now, both of my Gaussians are spherical. They're sort of circles. So this means that the covariance matrix is a multiple of the identity matrix. That's the only way you can get a spherical Gaussian like that. So that's just, at this moment, it's an instance of an identity matrix. But in general, this will be some matrix that reflects how the different attributes are expected to correlate with each other. So if you're having a bit of trouble with the matrix notation, there is nothing scary about this. You can write it out. You can just expand it out as follows. So that whole expression, you're summing up over pairs of attributes A and B. Right? You're looking at how much does the ith point, so maybe that point right there, how does that deviate from the mean of the red Gaussian along attribute A? How much does it deviate from the same mean along attribute B? So those are two different numbers. And I'm going to multiply them by the element AB in the inverse of the covariance matrix. And that element in the inverse of the covariance matrix, the element in the covariance matrix tells me how attributes A and B are correlated overall. So not for this particular instance, but over the entire data set. How are they supposed to be correlated? So you're sort of normalizing those two individual deviations, the deviation for attribute A and the deviation for attribute B, by the expected co-deviation of A and B. That's the way to interpret the inverse of the covariance matrix. But overall, this quantity is just, I'm shooting at the red Gaussian, what's the probability that my bullet lands right there? Okay, that's what you're computing. Next thing, you apply Bayes' rule, and you convert those probabilities to posteriors. Assuming that my bullet landed there, was I shooting at the red target or at the blue target? That's what the posterior tells you. So one way to reflect that is you could think of it as a coloring. I'm coloring each data point with the more probable color. So this point is, I was probably shooting at the blue, so it's colored blue. This one I was probably shooting at the red. All the points in between, there is some mixture of blue and red, same as on the previous slide. Now, the next step, this is slightly different. This is just for algebraic convenience. So I'm going to take those posteriors and convert them to weights. Right? These weights reflect how important a particular point is for a particular Gaussian. So it's the weight that associates instance I with Gaussian number C. And it's just the posterior divided by the sum of all posteriors. Right? It's pretty simple. It's think of it this way. Out of all the points that were colored red, how important is this particular point in relation to that? So that's the function of this weight. And then I'm just going to use these weights to recompute the means and the variances of the two Gaussian. So the mean for the Gaussian C, I'm going to compute it individually for each attribute A. So for attribute A, it's just going to be the average of the values of items that were assigned to Gaussian C, weighted by the weights that I computed in the previous step. So I add up all the values of attribute A across all the data points, and each value is skewed by the importance of that instance to that Gaussian, by the importance of instance I to Gaussian C. Same thing for the covariance, right? So the covariance, you just compute it in a normal way. I'm computing the covariance of attribute A and attribute B for Gaussian number C. That's the sigma CAB. So what I do is I sum up over all data points. I take, for the ith data point, I took the deviation, how far the ith data point deviated from the mean of Gaussian C on the attribute A, how much it deviated on attribute B, multiply them together, and multiply them by the importance weight. How important was instance I to Gaussian number C. And if you stare at it, you'll see how that's related to how we use the inverse, right? So it's kind of symmetrical, right? We're multiplying the deviations here and we're computing the expected deviation, and there we're taking the same product and just dividing, well, it's not dividing, it's a little more complicated, but it's trying to normalize out the covariance of those attributes A and B. So that's how you compute the covariances, and the only thing left over is the priors. So the priors, it's basically how many points did I have assigned to Gaussian number C. So the way you compute that is you add up all the posteriors, so the amount of color C in the coloring, and divide it by the total number of data points. So it's the same example as on the previous slide, only previously we had one-dimensional data, and this is for arbitrary dimensions. All right, so if you run through it, it might look like that. So that's the coloring. The Gaussians that are fitted might look like that. So the blue Gaussian is trying to straddle all the blue points. The red Gaussian is trying to straddle all the points that have red in them. And then the next iteration, the blue Gaussian is probably going to lose that point that is closer to red. That is, if the slides ever decide to render. Yes, so something like that. That's something that you might expect of running an EM algorithm with two Gaussians on the dataset above.